Alright, so we now know how to calculate both the magnetic force on a current carrying conductor and how to calculate the magnetic field strength of a current carrying conductor. So what we can do is we can take two parallel conductors. We have one wire and a second wire, and remember they got to be parallel. This allows me to get rid of this cross product here. And so we know how to calculate this magnetic field strength using this formula here. Because if we look at the ends of the wires rather than looking at them parallel like this, since the magnetic fields loop in a circle around the wire, remember they got to be closed loops, we can calculate the magnetic field that this current carrying straight conductor will exert a distance r away, which the other straight current carrying conductor will be in that magnetic field. So essentially I can take the force formula and magnetic field formula and I can put them together here. But we have to remember, we have this one here that is exerting the force. So we'll call that I1 over here. And then we have one that is experiencing. So we'll call that I2. So we'll make this a 2 here. So you'll have to have one current straight carrying conductor that exerts the force and the other to experience the force, it being some arbitrary distance r away inside the magnetic field of the other wire. You can't exert a force on yourself. We learned that back in 151. So subbing those two equations together, we get that the force per unit length, this is traditionally how this equation is written, so force per length, is equal to our magnetic constant times our two currents divided by 2 pi r. And we have to remember, if the currents are in the same direction, the wires attract. And if the current is in the opposite direction, the wires repel. You should pause here and look at example D on page 3 of your chapter 28 lecture notes. And once again, I remind you, please try the problem first, then look at the solution in the next video.